today is the 30th lecture of session of this lecture series, and I would like to invite the Vice President, ISL, Engineer Mrs. Kamala Gunwardhan, to do the welcome.
Am I audible, Bandhuka?
Yes, madam.
Yeah, okay. Yeah, thank you. Thank you, Bandhuka, for your invitation. And I'm proud, actually. I'm really proud in welcoming you all, especially Professor Tishant Jayasinghe, who is helping us all the time. He was with the Civil Engineering Sectional Committee for now continuously 3 years, once as the chairman, then he was continuing our lectures. So now this is the 3rd year. As continuously is sacrificing his time, if I say like that, I think it's really correct. Devoting his time, doing the papers, doing all the lectures very effectively. And there's no issue that we can judge it with the participation of our participants, the number and their enthusiasm to get the things done. So I think I'm really happy to do this honor. I welcome Professor for the lecture today and also the online participants. So with that, I think this is, you are continuing with the previous lecture, lightweight hybrid multi-story construction. That one, no, Bandhuka, we are doing?
Yes, madam.
Yeah. So I think without taking much time, I will welcome everyone to the lecture and have a good day. Professor, over to you.
Yes.
Thank you.
Thank you. Thank you very much.
Welcome.
So, a very good evening to all of you. Last time we started talking about the design aspects of lightweight hybrid multi-story construction with the design of slab system. The slab system. So today's lecture number 13, date is 6th March 2024, page 1. So if I recall what we talked last time, we looked at this lightweight system. I explained the way that things happened since Second World War, the historical development, and why people changed to solid slabs and flat slabs from bib slabs. This is the in situ cast concrete. And then we looked at this possibility of having a link like this, because we did not want to have connections only through bond. We always wanted to have a positive connection. So we run a 8 mm bar that way, and then we have a bar to lock it, and then we have the top reinforcement for the slab running up to 0.3 3L. So this is 2 meters. So we can have this top bar over a length of like 600 millimeters. And it's a H8 bar, 8 millimeter bar. Here also we'll have a bar like this. Above this, here 600. That is a H8 bar. And we said that because of all these reinforcement, the slab will behave like this. So we can design the slab for WS square 10, WS square 10, and what we showed was even for 5 kilonewtons per meter squared imposed load, what we want is 1 H8, but we provide 2 H8. This means that we can actually go for even 7.5 kilonewtons per meter squared load on this slab system, provided the beam is strong, has adequate. So that is the scenario. So let's look at a typical application by looking at a house plan of a large house, so that I can show you the real applications. So let's see that, let's take an example of a house having something like the garage, maybe 6 meters this way and about 6.2 meters this way. Then we have an entrance lobby and a bedroom. So let's say this is about 3 meters. This is about 4 meters. This about 3.5 meters. And then we may have this 3.5 and 1.5, something like this. The entrance, washroom, and this is an arch. Then we have the staircase. Here we have a garden. Here we have the staircase. So this is about another 5.7 meters. And on this side, let's say we have the wet kitchen and a pantry and a bedroom which attach washroom. So let's say these dimensions tally these ones. So these 1.5 and these is about 3.5, and that is here you get 11 meters. 6 plus 7, 13 meters. So it's 5 meters. 13 minus 5, so we get 3.5, 4.5. So let's assume. So I just want to show you the possibility. And here we might have the living area, large living area. So what are the possibilities? First, we'll take this example. One possibility is running this beam this way and having slabs this way, 2 meters. There is a possibility of running the beam other way as well. And then here, if you look at this one, 6 meters. So we have the possibility of running the beams this way. Having the slabs like that. Here, every 2 meters, we can run a beam. So every 2 meters. So when I say 2 meters, you know, we run the slabs this way. These rooms, we have the possibility of running the slab this way, because this is going to be something like 4 meters. So we run the slab this way. So these are all possibilities. And the washroom we can run this way, because we need a drop. So here also washroom can be run the other way. So when you look at this example, we can identify two typical situations. One is the beam is spanning something like 3.5 to 3.5 meters. Another case is beam is spanning 4.5 meters. The other possibility is beam is spanning 6 meters as a typical case. So, and in a house, the imposed load can be 1.5 kilonewtons per meter squared for bedrooms. It is 2 kilonewtons per meter squared for living, dining, pantry, and so there isn't a big difference between 1.5 and 2. So for the design of the beam, we can consider something like 2 kilonewtons per meter squared. Banduk, is that clear?
Yes, that is clear, sir.
Yeah. So I'm taking a typical example so that we can
Yes.
provide the answer for a real case, right?
Yeah, that is fine, sir. Okay.
Right. So now we have to see. So we'll take the simplest case, 3.5 meters, and this page number 2 of 6th. So if you take a typical case, now another thing that you can observe here is, now this may be a blind wall. That is a blind wall. You can see all these slabs can span onto the wall. Here also it can be an opening or whatever, but it can span onto the wall. But here the chances are, here we'll get a big opening for the cars. So these were the cars. So what are the chances? So we can have a column. Now, when it comes to the column, we have a debate. What is that? 9" to 25 by 2. 25 column, or if you are using this strong block work, because we want to make the structure as light as possible, so we can have the standard SLS 855 complying block having a length of 390. This 390, this 150, height is 190. So a block of this nature, hollow block, will cost you about 150 rupees at the factory. At the factory, it can cost about 150 rupees. And it covers about close to 0.8, close to 0.9 square foot. Close to 0.9 square foot. Area is covered by each block. So in a moment, I'll show the cost aspects, but first I'll discuss. Assuming that we are going to use this lightweight material, but the important thing is the compressive strength of these blocks can be about 5 megapascal to 7 megapascal. So when I teach masonry design, how to undertake masonry design for Eurocode 6, you will understand that once the unit strength is known, generally we use M4 mortar. M4 means 4 megapascal mortar. So use M4 mortar and do the construction. We can get a strength of about 3.5 to 4 depending on the block strength. So these blocks are, if you use a similar masonry wall out of the type of bricks that are available in our market, the maximum strength we can get is 1.5 megapascal, but with these blocks we can easily get around 3 megapascal wall strength. So the wall strength is doubled, but the weight is much lower because these are having holes, hollow blocks. So the density is 12 kilonewtons per meter cube. The density is only 12 kilonewtons per meter cube. So density of the block is 12 kilonewtons per meter cube. So general density of masonry is 20, whereas these blocks has only 12 kilonewtons per meter cube. So the overall weight of the wall is less, strength is more. So we can run a beam here and support this support the beam can be supported by using two L-shaped columns. So these 300. Now the beauty of this L-shaped column is it is very strong. It is stronger than a 225 by 225 column because it cannot buckle easily. Each side is 300 millimeters. So this side is 300. This side is 300. The area of the column is more than the area of a column like this. The area is more. So it is like the area is equivalent to a 300 by 225 column. Area is small. So what you find is this particular column has more strength, but most importantly, it can be flushed with the wall. Wall is 150. So there's a particular advantage because you can't see the columns. You can't see the columns. So we might run another column here and another column here. Why? Because we might need a beam here. Because this can be a window opening, connecting the garage with the window. Similarly, we might need a column here and a column here and another beam this. Why? This can be a large window opening to the garden. So wherever there's a big opening, we'll use whenever there's a big opening, we'll use columns. So we have a column here. We have a column here. Similarly, we can say because this outer wall might have a lot of openings. So we can have some columns there. Some columns there. Run a beam here. Why? Because we have columns and large openings. These are openings, large windows, doors. But here we have only small openings. So though above those we can have lintels. So we don't need many columns on this wall. And similarly, we might have a big opening here. We might need a column here, run a beam, and we might need running another beam this way, and we might need a column so that we can run a beam this way. Now you can see we have few columns, but the beams are run only in one direction. So there is no beam here. No beam. The wall can straight away take the weight of the slabs. And here no beam. So wall is taking load bearing wall. These are load bearing node. So these are load bearing node. These are load bearing node. Because we don't have any openings on that side. These also load bearing. These are all can be converted to a load-bearing wall if you are going to place the beam this way and run the slabs this way. But in this case, though it can be a load-bearing wall, we are not transferring a lot of load to those. Is that clear, Bandhuka?
Yes, that is clear, sir.
Yeah. So basically, we have a lightweight material. And when you look at the vertical load transfer, we have the concrete frame structure partially. What is the rest? Rest is load-bearing masonry. So we call it hybrid system. Because in a normal multi-story house, we try to transfer most of the loads onto the frame structure and use masonry as a primarily as a infill material. But in this particular system, by using a masonry which is strong, very strong, what we do is we are transferring the loads onto the masonry and onto the concrete, and we are sharing the load of a lightweight slab system. We are sharing the weight of a lightweight slab system. So in this lightweight hybrid system, we are using masonry of lower density because masonry has holes, hollow masonry. But it's super strong. It is twice as strong as brickwork. Right? But it needs much less material. So what is the main problem we have today? The main problem we have today is the cost of sand. Why? In Sri Lanka, we mine the sand in Manampitiya. From the river, sometimes it's mined and it has to be brought over 250 kilometers in lorries, where the maximum the lorry can give is 3 kilometers per liter of diesel. So, if you take 1 cube of sand, it is rupees 22,000 or above. And the transportation, the diesel is around rupees 350. So close to rupees 125 goes for per kilometer, goes for diesel. And then per kilometer cost is about 200 is the per kilometer cost when you consider tire wastage, all the costs. Because sometimes that one tire can cost close to 100,000 rupees. So how much money we spend? 50,000 rupees to bring a big lorry carrying about 4 to 5 cubes. So you can see why. So out of this, a street value of 110,000 for 5 cubes, 50 to 60,000 goes to about 50,000 to 60,000 goes for work. tire wastage. Salaries. So when you look at all these things, sand is priced as rupees 22,000 a cube per cube. 1 cube is 2.8 meter cubes. So 1 meter cube has a cost of what is the cost, Banduku? 22,000.
7,857.
7,000
857.
rupees. And 1 meter cube has sand as a bulk density. These are the solid material we buy. We buy the bulk material, 1,500 kilograms per meter cube. So 1 kilogram of sand, what is the price? What is the price of 1 kilogram of sand? 1 kilogram of sand is about 5 rupees. Is that right?
Yes, 5.24.
Yeah. So let's say we, after allowing for wastage, 550. Because when we say we are buying 1 meter cube, we might not get it fully. So we can say the cost is about 550 rupees per kilogram. Per kilogram. Now you can see the crisis in the construction industry. We pay 550 rupees per kilogram of sand. Can you see the problem, Bandhuku?
Yes, yes, sir.
And out of this 550, about 4 rupees goes for transportation. That we never thought, right? So we have a huge crisis. And then what we do is we try brickwork. We try bricks. So what is the size of a brick? We have non-standard bricks, about 100 millimeters wide, 50 millimeters thick, 200 millimeters long. Slightly small. Slightly small. The standard brick should have a height of 65, but here we have only 50 millimeters. So now we try to do the brickwork. So we get around 15 millimeter, 10 millimeter mortar, and it's customary to have the English bond. And we run the next layer. So with this size, we need about 15 bricks for 220 millimeter wall, maybe 210. 15 bricks for 220 millimeter wall at rupees 25. plus mortar. So 25 into 15 come to 375 rupees plus mortar cost or labor cost. When you add all that, 1 square meter of brickwork can cost about 9,000 rupees. Whereas, if you look at this lightweight block work, the block has a cost of 150. So it needs about 175 rupees, 175 per square foot, plus another about 50 rupees worth of mortar, plus another 150 rupees construct. So you can see it comes to about 250, 225, 325, 375, 400. So 1 meter squared of 150 millimeter block, hollow block. What is the cost? Maybe 4,500. So here we get 50% saving with 3 kilonewton, 3 megapascal compressive strength. Three megapascal compressive. That will allow hybrid construction. And we are using our lightweight slab. So we have lightweight, hybrid, but we can go for multi-story. Up to 4 floors. So you can see we can achieve a very significant cost saving. But the problem with brickwork is brickwork has so many joints. And how people generally apply pillar mortar on both sides. Make it level. So when you do that, we need a plaster. Very difficult to do the plaster for 15 millimeters. We generally do the plaster for 15 millimeters. Very difficult to do it for half an inch. It's little more. So we need about 15 millimeters. Why? Because we have so many joints. While constructing, though we try our best to construct it as vertical as possible, what happens is the brickwork tends to deform a little while the construction goes on until it hardens. So you'll find even if you have constructed the wall almost perfectly, one problem is there's a lot of mortar. So here you get mortar, here you get mortar, here you get mortar, here you get mortar. Every mortar. So a lot of sand goes, a lot of cement goes. So you find the cost of construction is very high, around 9,000 rupees per square meter. Whereas in the block work, we can reduce it to about 4,500 or sometimes even lesser. So how do we do this block work construction? Block has op. So we turn the block upside down, because in this block, bottom is solid. So we have this. Bottom is solid. So what we do is we turn it upside down. So what you see is a solid block when you turn it upside down, because hollow part is here. So hollow part is hidden. Then what you do is you lay it on a mortar bed. Thickness is about 15 millimeters, or it can be slightly more. Then after making it level, plumb, after checking the verticality, we use about 300 millimeter long a joist, 50 by 50, and we give a blow to the center. Blow to the center. What happens? These were wet mortar, M4 mortar, that is capable of generating a strength of 4 megapascal with 1:5 cement, sand. What happens? This mortar will squeeze into the holes in the block and lock it. We lock the block into the well compacted M4 mortar. So what do you get? You get a strong block, strong wall. Because of this locking, not much buckling, deformation during construction. So the block wall will be very straight. So if you look at this plaster, 15 millimeter plaster, they charge about 75 rupees per square foot. And it costs about 75 rupees for material as well. So plaster in 2 phases can cost about 3,000 rupees per square meter, or 150 rupees per square foot. On that, you have to do all the finishes. But here, we are getting a wall almost perfectly vertical. And what you do is, while constructing, you will use the sponge, and first you use the plane and level it, and then use a sponge and make it a perfect wall so that it will be ready to receive a thin plaster of 3 millimeter. So there's a cement-based plaster, manufactured with research done in Sri Lanka by a very innovative person called Mr. Dhammika from Padukka, and he sells this as Mako Super Plaster, which can be completed for a thickness of 3 to 4 millimeters, and these dolomite based. These dolomite based. So we actually helped him with when he was doing research at Department of Civil Engineering, because we saw the huge potential in his products. So this can bring a 20 kilogram bag costing about 1,000 to 150, purchased directly, can cover about 40 square foot, giving a cost of 30 rupees per square foot, which is a significant reduction from 150. So you get 150 versus 30 rupees, and there will be only a small, this is coverage is more, so the labor cost is less. So 300 rupees can be brought to about 100, 125, in the range of 125 to 100. So you can get a saving of more than 50%. Is that clear, Bandhuka?
Yes, that is clear, sir.
Yeah. So you can see in this system, we are saving wherever possible. First, we use lightweight blocks. But they are load bearing masonry. Having a strength of 3 megapascal or more of wall strength. Number 2, we use a lightweight slab system, precast slab system. Slab thickness 90 millimeters. And if you want, you can finish it with terrazzo finish, or you can make it so that with the overall thickness of 100 millimeters, you can complete the tiles. So including the tiles, the thickness will be 100 to 110 millimeters. So it's a significant departure from slabs of 125 to 150, 25 millimeters of leveling screed, and then tiles giving about 12 to 15 millimeters with tile bed. A huge departure from an overall thickness of, say, 125 plus 25 plus 15. That gives 165 millimeter. Or it can go up to 150 plus 25 plus 15, 180 millimeters. So an overall thickness of 165 to 180 is reduced to 100 to 100. So can you see why we call it a lightweight system? Mandukar? So slabs are lightweight. But some of the slabs can be directly supported by the load bearing walls. Can be directly supported by the load bearing walls. So you can see that's number 2. So we have lightweight slabs, we have walls, and we have frame carrying vertical loads, walls carrying vertical loads from slabs. So we call it hybrid. Because it's lightweight, three megapascal is sufficient to bear the load of up to 4 slabs. The weight of up to 4 slabs can be taken by these walls. Why? One is its overall thickness is 110 millimeters. So 110 multiplied by 25 plus multiplied by 1.35 plus 2.0 into 1.5. What is the value? 0.110 into 25 multiplied by 1.35 plus 2 into 1.5. What is the value, Bandukha? Point 110 into 25 multiplied by 1.35. So we are trying to find 1.35 GK plus 1.5 UK.
6.7
6.7 kilonewtons per meter square. Let's say this comes to about 7 kilonewtons per meter square. Is that okay? So we'll assume.
Okay.
But when you look at a wall, 150 thick. This is the precast slab. This is in situ cast. But there's a beam here. The span is 2 meters. So how that load goes here? So at each floor level, the wall carry self-weight. And in addition to that, it can carry 7 kilonewtons per meter. Then again, it will carry the self-weight. Then again, it will carry 7 kilonewtons per meter. So you can see this hybrid system can easily go up to supporting post slabs. Why? If you have a normal load bearing system, we might have a load of about 9 kilonewtons per meter squared. We have a load bearing wall. This may be about 4 meters. So half of this load goes there. So that means at every floor level, we are transferring about 18 kilonewtons per meter. So even with that, we can easily go for 2 story. But in this particular system, we have reduced the load on the wall up to 7 kilonewtons per meter. So because of that reason, we can easily use this system to go up to 4 floors, and even sometimes if you have done the construction carefully, you will find you can maintain a factor of safety above 4 with 5 slabs, with 5 slabs. So which means you have a house, ground floor, first floor slab, second floor slab, third floor slab, fourth floor slab, and even a roof slab can be supported. So this hybrid system is very efficient because of this particular slab system. Not like a solid slab, it transfers loads into both directions, but those loads are very lightweight. Is that clear, Vandana?
Yes, that is clear, sir.
Yeah. So the other advantage is we cast this like this. We cast the beam, the slab. We connect it, finish it with terrazzo, or we finish it with tiles directly on this. So if there's a minor variations, we can actually use a terrazzo cutter and cut it and then fix the tiles. If there's a little bit of unevenness, you can cut it with the terrazzo cutter and then fix the tiles. Or give the terrazzo finish with marble and broken windscreen pieces and all those things, and we can get a nice finish. Or else we can fix tiles directly on it. And what we can do is we can use this thin plaster as the soffit. 4 millimeter plaster instead of soffit plaster, because it's a putty. It can be cement based putty, not lime based. We can give a huge coverage. So we know soffit plaster cost of labor is high, because doing a soffit plaster takes much longer than doing a normal plaster on a vertical surface, because we have to do it hanging. So the labor cost for soffit plaster is much higher, but here we are using a putty, which means it takes much less time to cover the walls, cover the soffit, cover the walls. So it's super fast. Huge saving in labor is possible. So if you look at this versus conventional slab, we have the street 25 millimeters. Generally, even if you try to get 20, it's very difficult, because masons generally say they are more comfortable with 25 millimeters because they don't do the slab properly. So this is 125 to 150 meters. And then we have the tiling. And then we have a soffit plaster, another 10 millimeter. We have 10 millimeter soffit plaster. Then you will might have, but sometimes you can avoid soffit plaster if you go with plywood shutters or steel shutters. So that possibility is there. And then we have the tiling. So if you are using a macro superplast type of thing, there is no cost penalty on the soffit side of this system. There is no cost penalty. It's like using plywood formwork or steel shutters. And so in this system, when you are casting, there's no shutter because the panels are precast except props. We need props because I told you during the construction, we like it to be supported in the middle, each panel to be supported in the middle. So we need some props, but we don't need a shuttering. So there are, this lightweight system is efficient not because it's light, but it doesn't need shuttering as well. So in that sense also, it can bring about a sale. It can bring about a sale. So if you look at the overall situation, we save on the slab, lightweight, wall, lightweight, columns built into the wall. So no special plastering for columns. No special plastering for columns. Otherwise, plastering a column is also a costly item. But column is built into the wall, so no special plastering. Then walls are load bearing. Then walls, no thick plaster, only a thin plaster. Only a thin plaster. So we save a lot on this. Then how about the roof slab? Roof slab. Let's see how to do the roof slab. Because roof slabs we know a lot of waterproofing and all those things. But in this system, what we can do is we can enlarge the beam and make it behave as a rectangular beam and separate the slab and have a bitumen sheet. Separate the slab from the beam and then we complete it like this. So the slab is free to expand and contract. And even when it is supported on a wall, we will have a small lintel so that the wall will be separated from the masonry wall. The slab is separated from the wall, and on top of the wall we have a lintel. But roof slab. What is the biggest problem? Heat transfer. But why do you need a roof slab? Why? Why do you need a roof slab? Why can't you have a roof? We like roof slab because we build on 150 to 250 square meter lands or 6 perch to 10 perch lands. We build on these. So once you do that, so they are generally subdivided like this. So this is the road. This is narrow, about 10 to 12 meters. And we'll have a rear space. It's a must. We have to keep 3 meters at the rear. So if it is a subdivided land, there's no building line. So you can bring the garage up to this level. But you need to keep 1 meter distance here. And so you can bring the house up to that level. If it is subdivided land. Otherwise, if it is facing a main road, you will have a street light and a building line. So the building line is only 1 meter if it is subdivided land, like auction land. So we have very little space for garden. So many people like rooftops. But rooftops give a lot of trouble. So how to minimize the trouble given by rooftops? That is the important question. So separate it. With a bitumen sheet, separate it. Have the slab. So all the roofs leak because of lack of drainage. So we start with 60 to 70 millimeters. We finish with 40 to 45 millimeters. We create the drainage path with concrete. The moment you create drainage path with concrete, we have rains lasting maximum of 2 to 3 hours. All the rainwater is drained properly. You don't get a big waterproofing problem. That is avoided by providing good drainage. But still, it can absorb heat during the daytime. So there are two options. One is have a white color floor paint. On the white color floor paint, you can apply water-based varnish. You can apply water-based varnish. So the white color surface can be washed if it is dirty. The moment you apply, make it white color, what happens? You will absorb less heat, the absorption becomes 20%. And cement color absorption can be about 55%. So minimize the amount of heat transfer. But there's another very useful solution. And that solution is actually have a greenhouse. So the concept is we have a sloping roof, flat soffit, separated. There's a bitumen sheet, which is not a very good thermal conductive material. So this slab is free to expand and contract, and we can create PVC pipes, we can create small greenhouses with a zip here, so that you can open the zip and go in and attend to all your plants. And the concept of small greenhouses, rather than creating big greenhouses, you create a number of small greenhouses like 2 meter by 2 meter. The moment you do that, and then part can be covered with solar panels. Likewise, you can create, or you can use a big concrete cylinder with a base and plant some trees. So all those are possible. So that you can create a nice garden on the rooftop, because this system is capable of carrying loads up to 10 kilonewtons per meter. Because one of the biggest problems we face with slabs is, solid slabs is, they are not very good in carrying loads. They cannot carry up to 10 kilonewtons per meter. Whereas this can. So we create this system because it can carry up to 7. If you lay a polythene and lay a thin layer of soil, you can create a garden on the rooftop without having any durability issues. Because the roof is laid in a slope, then you get thick polythene and then cover it with soil, or cover it with large pots. So what is the penalty? To support all these big loads, we need a deeper beam at every 2 meters. So the normal beam may be this size. This may be about 50 to 100 millimeters extra. That is the only penalty. And you might find that instead of 2H12 plus 2H10, you might need 2H, 4H12, something like that. Slightly more reinforcement in the beam. So one of the biggest problems we faced with roof slabs was roof slabs are not capable of carrying big loads. But with the calculations we have shown, the system with 2 numbers of H8 bars can easily carry 5 kilonewtons per meter squared. It needs only 1 bar. We are providing 2 bars, which means it can easily carry up to 10 kilonewtons per meter squared. So without any fear, by strengthening the beams, you can create a nice rooftop garden, because we lose most of the land for the house. So we don't have land. So we create a land at the rooftop, because we have a very strong system. What do you think, Bandhuga?
Yes, that's correct, sir. That
Yes.
is correct.
So that is the future. But what is the most important advantage? The moment you go for a roof slab, it is cyclone resistant. Why? It's heavy. Heavy in the sense not very heavy, but it has a weight of around 3 kilonewtons per meter squared. But what is the maximum suction that a cyclone can induce? Maybe about 1 kilonewton per meter squared. The maximum suction that a cyclone can induce is about 1 kilonewton per meter. Even if it goes up to 1.5, still the roof is much more heavier than the uplifting. So automatically you get cyclone resistant building. And so this slab can give a solution to climate change. Why? With the climate change, to face the climate change, what is the best solution? Trees. On one side, they absorb carbon dioxide. On the other side, they add oxygen. And in addition, they provide shade. So the solution to climate change is given by this lightweight slab system, because it can be designed to carry 10 kilonewtons per meter squared. So without any problem, you can very easily create a rooftop garden with access without needing waterproofing, because you can rely on polythene laid on the roof, inclined roof. Only the top surface is inclined if you are going to lay soil on it. On the other hand, if you are going to use pots, then you don't need any polythene or anything. You can directly support the pots with the bottom with a large bottom on the concrete slab. And it has good drainage properties. If you cure it properly, you can get a very good, very high level of very high strength, impervious surface. And if you apply a water-based varnish on it, then it will not absorb any water either. So, and then you can create some shade either in the form of greenhouses, which would be much more effective than using soil, because greenhouses are not, when you grow vegetables in greenhouses, parrots cannot attack the crop, because one of the biggest problems in Sri Lanka is parrots stealing the crop. So that also can be minimized to a great extent. So now you can see the biggest challenge is designing the beam. Designing the beam. Because slab is not a problem. Slab is not a challenge. Slab is a gift. The challenge is the beam. Beam is a challenge. So next week, we look at how to design the beam and how to make it as optimum as possible, and what are the theories for rooftop supporting beam versus beam supporting an ordinary floor slab. And also, if somebody needs a flat soffit, we'll talk about how best we can achieve a flat soffit as well. Is that clear, Bandhuka?
Yes, that is clear, sir.
So we'll, because we need a lot of time for explaining the beams, so we'll postpone the beams to next week. Okay?
Okay, sir.
Right.
Um,
So how
yes,
about the questions?
Yes, sir, how can we reduce heat radiation under the roof? That's one
Yeah,
question.
that's what I said. I mean, shading is the best way. So shading can come in the form of large concrete pots filled with soil, because this slab has no restriction in carrying loads. So we can have heavy loads as long as the beam has been designed for that. So we can easily have large pots with soil filled in it. So basically we need some kind of shading. So it can be solar panels, it can be greenhouses, it can be uh, flower pots or pots, whatever. What we need is some kind of shading device on the roof so that we can minimize the solar gains. So because the roof slab is separated from the beams, there's no positive connection. The thermal contraction and expansion and contraction can take place readily. So there are two options to minimize the solar radiation. If you are not going to access the roof very often, we can paint it with brilliant white, and then it can be a floor paint or even emulsion would do, provided we cover it with a water-based varnish like Jet Holdings varnish or Nipolac varnish. So they will all this gives a thin layer. You know, when you are painting vehicles, after applying the paint, we apply a thick pot of lacquer, 2 pots of lacquer. So similarly, here also we apply a protecting coat. The moment you do that, the heat transfer will be minimal. Okay, Bandhuka?
Okay, sir. That is clear. And also, there's one question. We can use a lightweight hybrid system for maximum 5 slabs, but if we need multi-story, more than 4 floors,
That's a
what
good
can be the
question.
solution?
Actually, this is a system that can go up to 12 floors. So what is the penalty? What is the problem? What is the problem? What is restricting? So restricting is, we have gone for 150 wall, hollow concrete. So why can't we go for 200 millimeters in the lower floors? And these 200 block length is 390, 200 wide. It has thicker walls. The walls are thicker. So you have a groove. Walls are thicker. So these out of concrete, chip concrete. Let's say you need 8 megapascal block. Then you can request a company like ICC. What they do? They have to provide you with 8 megapascal block, and you can use inform mortar 1:5, cement, sand. So here you can buy mix river sand with manufactured sand. The manufactured sand also can have a little bit of pozzolanic reaction to get a very strong mortar. And now what you do is you go up to 8 floors. First 4 floors you use ground floor. You might use 8 megapascal block because it can be slightly more expensive because what they do is they use more cement. And somewhere here you might use 5 megapascal block because it's strong. Then later you use 5 megapascal block of 150 thickness. So my perception is we are doing some research on this because there are undergraduate projects running to determine the maximum number of floors. So one project is 8 to 12 story range. Another one is 4 to 8-story range. Another one is up to 4-story range. 4-story I have done, but this project is done to document everything properly, so that it can be presented at research papers. Maybe research papers on engineering or international conferences held in Sri Lanka or whatever, so that the whole engineering community will be able to make use of the available information. So, have I answered the question, Bandhuga?
Yes, sir. It's
Right.
clear. Yeah.
It's clear, right?
Okay.
So basically, you can see this is a wonderful system because it saves in many ways. Number one, it is less material. So it can give about 50% saving because it needs less steel, less concrete, less formwork. So that is a lightweight slab system. Secondly, reduce the number of steps. That means no leveling street. No leveling street. Number three, we rely on concrete to carry load in columns of L shape. Why? L shape column has more concrete area. It does not buckle. Easily. Hence, we need only nominal steel. So we can use 10 millimeter bars. In columns, the column goes like this. So you need a link like this. We need another link that can go like this. We need 2 more bars. Here we tie the link with binding wire. Here binding only. So it needs 5 numbers of 10 millimeter bars. It needs 5 numbers of 10 millimeter bars. So here number 1, 2, 3, 4. Why we can use 10 millimeter bars is the minimum steel content is 0.2% in Eurocodes. And Eurocodes also allow 10 millimeter bars in columns. And these are lightly loaded. Because we are not relying on the column alone to carry all the loads. We have hybrid system, so we can consider these columns as lightly loaded and go for a minimum amount of reinforcement in the columns. Whereas in normal 2-3 story building designs, you try to transfer all the slab loads onto columns. So you can, it's very easy to see engineers using 16mm bars or 12mm bars a lot in columns. But here, what you get is only 10mm bars, and you can use 8mm links at 20 times diameter spacing. So when you use 10mm bars, 8mm links can be used at 200mm centers. 200mm centers. And so what you do is, when you're doing the column reinforcement, so this is the flow, this is the flow, your column, L-shaped column. We provide 4 numbers H8 because Eurocode says steel must be YK should be 600. So if you are doing a strictly for Eurocode, you have to use H8. But if you are doing the columns for British code, then you can even use my steel 6mm bars. But the cost penalty is not very big, so you can use this. Beyond this, 200 centimeters. These bars are 10mm. Again, here you will have 4 bars at something like 50 to 75 spacing. What is the reason? If it is subjected to an earthquake, this is a frame subjected to earthquake. Where to get the plastic hinges formed? And in the beam, you can get it here. So in the zone that the plastic hinges can form, we provide higher confinement. So we create a triaxial stress state. The moment you create a triaxial stress state, if you test a cube, uniaxial, it goes like this. Triaxial, it goes like this. And we know this is a stress strain curve. Stress strain curve. So the area under the curve is the energy that the concrete can absorb before it crushes. So the moment you create triaxial stress state, it can absorb a huge amount of energy so that we can prevent crushing of concrete by increasing the confinement. And H8 bars are very good for enhanced confinement because they don't yield easily. So they can confine the concrete and keep it. So we have a very very lightweight, lightly loaded columns, but with high ductility. Anyway, in an earthquake, lightweight structures absorb less inertia. So earthquake loads will be less. And if you look at the plan, what you see is walls everywhere. So all these walls will be shear walls. So what can you say about the earthquake induced deformation, lateral deformation, very small, because it's not easy to push a masonry wall that is heavily loaded and strong. Masonry is a strong material because we are using very strong masonry. It's loaded, masonry is loaded fully. Then it's very hard to fail a masonry wall, because what happens is, in an earthquake situation, what happens is, we have a frame, we have an infill, we have beam or a slab. So we have the columns. Now we are pushing. So what happens? Masonry will go into tension. Compression in one direction, tension in the other direction. So tension in the masonry can cause cracks. But heavily loaded. Moment it is heavily loaded, these cracks cannot open. And then the frame will start to move like this. So the mason here will be subjected to heavy stress. But we are using a concrete block, having 5 megapascal or above. So it's a concrete block, no mortar joints, very few mortar joints, even those mortar joints are well compacted. Because I told you we are going to tap it with 2 by 2 joist, 2-inch by 2-inch joist. We tapped it, we compact it fully. All these levels, it's compacted. So it's a very strong wall. So what happens is, when you apply the lateral loads, because masonry is loaded vertically, the deformation of the masonry wall will be minimum. So the movement of the building will be minimum. If the movement of the building is minimum, there's no way the concrete can crush, because the strains in the plastic hinges will be very small. So by providing enhanced confinement, we can make the columns extremely ductile, and hence they can absorb huge amount of energy before the concrete crushes. Is that clear, Mandukar?
Yes, that is clear, sir.
Right. So with that, shall we conclude?
Okay, sir. Okay. Thank you very much, sir, for your commitment in conducting this lecture series. And I believe this lecture series is a remarkable lecture series in our community for those who are interested in value engineering and cost-effective house construction technology. The questions and the responses from participants tell about that. And also our YouTube uploads related to this lecture series are reaching thousands of views. So that is also telling us that we are spreading the message. So thank you very much, sir, for that. And also, I would like to thank Vice President Engineer Mrs. Kamala Gunawardena for your presence today, and also the Chairman Civil Engineering Sectional Committee, Engineer Mangala Silva, who is guiding and giving leadership for this lecture series for this year. Thank you very much, sir. And also, I would like to thank the ISS Secretariat, the Publicity Department, and the IT team for their support in hosting arrangements. Thank you very much. And also, I would like to thank all the participants for their continuous participation. That means a lot, and it is very important for the success of this lecture series. Thank you very much, and good night to all. Thank you, sir.
Yes. Okay. Thank you. Thank you.